Hello, welcome to this week 8 class. So it's 2 minutes to 7 p.m. So I'll wait for 5 more minutes to see if people join in and then I'll get started with today's session. Okay, so it's 7:05 already, and since one of you have joined this call, so I'll get started with today's session. Welcome to this week 8 session on traffic engineering. This is the TA session on the contents that were covered this week. So, since not many people have joined in this session, I'll just keep the discussion for the general audience and probably will be solving some of the problems that we'll be finding in the assignments and related questions, not exactly the assignment problems that you'll get. Okay, so I'll turn off my video and share my screen and start with one problem in today's class. So let me share. Okay, so hope my screen is visible. So here in this week's discussion, the topics that were covered were actuated signals, signal coordination, and oversaturated signals and mitigation strategies. So I'll be probably mostly focusing on problem solving in this session. So I'll start with actuated signals, and I think the very first question that you'll find in the assignment, not exactly that, but similar to that I'll be solving here. So the first problem that you have, so I'll give you a data. So for an actuated signal, so I'll write down the problem. Presence detection with 95 feet detection length is used on an intersection approach. Now, front edge of the detector rests on the stop line. So assume uh, head-to-head spacing between vehicles in queue in equals 25 feet. Startup loss time is 3.5 seconds. Then you have saturation here equals 2 seconds. So you are asked to estimate the value of G min high in seconds. So this is the problem that you have, and I think this was covered in the very first module of this week's content. So to solve this problem, this is directly related to what we discussed in the, I think, classes. And the formula for G mean high was directly given, I think, in one of the slides, where it is dependent on the startup loss time. It is also dependent on the distance between, okay, was there any answer on anything? 3.8 second you are mentioning. Okay, maybe I'll just see if that's the correct or not. Uh, yeah, but I'll keep the discussion for all the audience, whoever will be seeing this video later. So let me go step by step. So this distance between the detector and stop line is something which is known as D, that is used, and then there is assumed head-to-head spacing between vehicles in queue, and then you have the saturation headway which is assumed. So here the formula for G min high is L1, which is the startup loss time, plus you have the saturation headway, which is, you can write it as S suppose, times, then you have to take the integer part of this. So in general, when I mean, when I say integer, you have to take the seal of this. So it's that not just the integer part, but you kind of round it up to that higher integer that you have. So you have this d divided by the head-to-head spacing that you have in vehicles. So this is 25. And then you have another term which is plus 2n. But I think that's not relevant here. Yeah, the plus 2n terms comes in relation with the, I think, number of vehicles stored in the detection area. But, but for this problem, to solve this, you have this int d divided by this 25, and you have that s as well. So you can write L1 equals 3.5, which is the starter loss time, and then you have the saturation headway, which is 2 times this. You can write it as int. Then you have the d, which is the presence detection with a 95 feet detection length. So that's 95, and then you have to divide it by 25. So that's pretty much it. That will give you the answer, and that's 3.5 plus 2 times. So here it would be 5, sorry, it would be 4, because there will be 4 vehicles that are kind of, they are needed to be serviced. So it's 3.5 plus 2. So I think there is something. Yeah, that's correct. So you have 2 times 4, that's 8, and then you have 11.5 seconds. So that's the correct answer to this. So 3.5 was not the correct. 3.8 or whatever. I think, yeah. 3.8, 10.8. Okay. None of them were correct. So the correct answer is 11.5. So yeah, that's the correct answer to this problem. Uh, you have to be careful what is out there in the slides, and accordingly you have to put the formulas here and check whether these numbers are correct or not. It's not always this is 2. I think in the slides it's kind of misleading because it's written as 2 times this int of t by 25. So this values might change as well. So here, this, if this was 2.5, you would have need to be multiply this with 2.5 as well. So that's the first problem. And the second part of it can be is that estimate the value of G min. I think it was G min low. Let me check assignment problem once. Yeah, so yeah, you are asked about this. Okay, so for this one, again, there is a different approach to this problem. It's not like straightforward like the previous one, but it's not also that difficult as well. So here for Gmin low, I think this was discussed in one of the problems in this week, where one of the steps was to this finding out this Gmin low. So here you can write Gmin low as this L1 plus, here it's 2 because the saturation headway is 2. I can write it as S times some value which is N. And here this N is something that you have to find out. So here you have to just take the, you have to take into consideration of one vehicle. So that's kind of detecting something, right? So it's just one vehicle if you detect it. So that will give you this Gmin low. And that's why N, which is here, is 1. So L1 is 3.5 as before, this is 2 as before, and this is times 1. So this will be 5.5 seconds. So that would be the correct answer for this problem. So yeah, I hope this would be clear. And in the assignment problem, it was, I think the numbers are different, but the, I think the ideas and everything will be similar, how to solve it. Like, I think the head to head spacing, it's given as 20 instead of 25. And the length is also, I think, different and so on. So yeah, but I think it's very easy to solve this kind of problems. So let me now move to another problem. I think that's again relevant to the next question that you may find in the assignment. So let me get the data for that. Okay, so formula for G mean high and low. You will find it in the slides, right? And I have also written it here. So I hope you'll get it. Like this I have written. This is the formula for G mean high. For G mean low is n equals 1 that you have to consider. That's all. Next is the next problem. Let's see what it is. Yeah, so this is something related to, I think, semi-actuated signal, and it's a two-phase signal. So let's actually solve it. So it's on semi-actuated signals. So the problem is for a two-phase semi-actuated signal. So there is one table that is given to you. So let's so here this is phase. Next is green split. Next is change interval. Okay, this should be 4. And then you have clearest center. Okay, so this is actuated phase, or you can write it as phase A. Green split is 12. So this is 3. Oh. And then this is 1. And for non-actuated, phase B, this is 28, this is 4, this is 2. So now you're asked, okay, the minimum green time for actuated phase that's given to you is 8 seconds. To account for peak cycle by cycle demands, a multiplying factor of 1.5 is chosen. So now you're asked what is the value of critical cycle length. Okay. So that's the problem that you have. Now you have to solve it, and I think it was similar thing were discussed in the class. So let's see how we can solve this kind of problem. So it's, I think, not directly related to the initial portions, but somewhere I think second or third module of this week, this is discussed. So basically what you have to do, you have to check for some G max of this first phase and whether that's greater than the minimum green time of the actuated phase that's given to you. And then you also have to check for this G min of B, and then basically you have to sum those up and also sum the change interval times as well as this clearance interval times to get the total like value of the critical cycle length. So that's the idea. So let's see how we can solve it. And you have to also consider this 1.5 multiplying factor for this peak cycle bicycle demands, and that should be coming into the calculation for the actuated phase, as well as I think for the non-actuated phase as well. So that's pretty much it. So let's see from where I can relate it to the contents that were covered. So let's see. Yeah, so the green split are given to you, and then what you have to do is you have to find this G max of A as well as G min of B. So what will be these values? Uh, like if anyone is calculating, then that would be great. Because always when I solve it, I get a different answer from others. So yeah, hope someone gets it correct this time. Search. Okay, so it's 18, 42, 70, 18 seconds is greater than Shemin. Okay, so I think that should be the correct answer. Let's see. For the first one, it's, as you have mentioned, it's 1.5 times 12, so that's 18, and this is greater than Gmin of A, which is equals 8 seconds. That's given to you, so that's fine. This is 18 seconds, and here you have this as 42 seconds. Now it's just simple addition that you have to do for finding out the critical cycle length. So it's again, this is G max of A plus G min of B. Then you have this YA. Let's write it as capital. And then you have YB, and you also have this. Okay, so actually this is small y, and when you calculate capital Y and YB, you include those clearance intervals as well. So this would be, this is 18, this is 42, this is 3 plus 1, and this is 4 plus 2. So this becomes 70. So that's 6 plus 4, yeah, this is 70 seconds. So that would be your answer, which was correct, that were given in the chat box. Yeah, so this problem was very simple, and I think, let me see what were the exact numbers in the assignment. I think shouldn't be too critical. Okay, so here it's the multiplying factor is somewhat different. Yeah, This is see if this is it. 63 plus 8. Yeah, so one of them will be the correct answer. So the options are fine. Okay, so let me move on to another discussion then. So this will be another problem, and it's not exactly similar to the assignment, but yeah, there is one problem that's kind of close to the one that I'll be solving right now. So it's about this signal, this multiple signals and calculating the offsets and so on. So let me write it down. This is on some numericals. So this is, you have three signals. This is signal A, signal B, and signal C. So they are closely spaced to each other. So this is something like the signal coordination that you have studied, with distance between two consecutive signals being 200 meters on an urban arterial. Now it is desired to establish offsets between these signals for signal coordination. So let me actually write it as signal coordination. So considering the primary flow only in one direction, having two lanes and bandwidth efficiency of 36%, the desired progression speed is 45 km per h. Saturation headway will be taken as 2 seconds per vehicle, and the startup loss time as 2.5 seconds. Okay, so now this is the overall problem data. Now we are asked different questions related to this. So one of them could be to what is the ideal offset? Let me write it as data. Just the ideal offset between signal A and signal C, assuming that vehicles arriving at the upstream intersection are already in a progression that is moving platoon at the initiation of green. So the data might feel, or the problem might feel a bit intimidating because there are too many information here, but let's solve it step by step. So basically what is given to you is that there are three signals which are spaced at 200 meter. Now you have to finally check for the ideal offset between signal A and signal C. So if you take signal A and signal C, their spacing is 200 plus 200, which is 400 meter. And then you have some desired speed or the progression speed, which is given as 45 km per h. And from where you can find out like what would be your ideal offset between those signals. So this offset value is in seconds. So so you don't need all the data for this problem. So maybe I'll solve it in the next slide. Maybe you can take a picture and then try to solve it. Then I'll solve it in the next slide. So this is called as the ideal offset. So as the first vehicle of a platoon just arrives at the downstream signal, the downstream signal turns green. And the way to calculate it is this T ideal is L divided by S, where S is that average speed or the progression speed that you want to have, and L is the distance between signalized intersections. So it's just adding those two up, right? Now, if the vehicles were stopped and had to accelerate after some initial startup delays, so then that startup delay has to be added. But I think here, in the at the initiation of the green, uh, there is no kind of that is not considered as such. So that's why you don't need to add L1 here. So I think a similar problem was also there in the class where I think there are multiple signalized intersections that were spaced at different distances and desired platoon speed were given, cycle length, effective green and everything was given. And you have to first find out that T ideal, which is L divided by S. So that's very simple for the first problem. So let me see if anyone got the answer. It's 32 seconds, is it? Okay, let's see. So this is on signal coordination. Let me just recheck the data. Yeah, so the L, which I am considering, is the distance between signal A and signal C. This is as L, and this should be 200 plus 200 meters, which is 400 meters. And then you have the progression speed, which you can write it as S, and then this is given as 45 kilometers per hour. Now you have to convert it into meters per seconds, because ultimately you need L divided by S, and the unit of L is in meter. So this is 45 divided by 3.6 meters per second. That gives you, let me check, 12.5. So now you have to just get the T ideal, which is the ideal offset. This is ideal offset equals this T ideal. This is L divided by S. This is 400 divided by 12.5. That much seconds. So I think that gives you 32 seconds. Yeah, that's the correct answer. I think, yeah, in the chat you got it correct. Okay, so let's get into the next uh, question. So this one was relatively simpler, I think. So the next one is asking you for adjusted offset between different signals, not between, say, A and C. So let me write down the next portion. So what is the adjusted offset in seconds again between signal A and signal B, assuming that an average Q of two vehicles per lane is expected at the downstream intersection so that is signal B at the initiation of B and then you have you can assume vehicles are arriving at the stream intersection that is at signal A are already in preparation. So that is the moving platoon. At the initiation of the beam. Yeah. So you can stare at this problem again and try to solve it. Then I'll solve it in the next slide. So it's basically you have the T ideal right now. You have to find the T adjusted. For that also you have a formula, but here it's not between the same signal A and C. Here it's between A and B. And you have to again calculate the distances between them. So that's the modified L in this for this problem, and S is something that you already know, which is from the previous problem itself. And then you need to have some additional things into account. One was I think it's related to the startup loss time that were mentioned. And then you need to have this saturation uh, flows and headways. So that were given to you. Saturation headway was given. So, and have the Q value as well, I think. So let me check. Saturation speed. Okay, so let's see how to solve this. First, let me check the slides once. The T ideal is simple. Then we have T adjusted. So, so you need to consider this saturation headway, startup loss time, as well as queued vehicles per lane. So let's see if it was given. Okay, so you have average queue of 2 vehicles per lane. So that value is also given to you. So that's queue values. So the rest is just application of the formula. I think, yeah, one of the questions were also asked in the slides as well about this, and it was pretty straightforward. I think this is from the slide itself. Okay, so let me solve it in the next slide. So you have this T adjusted or this adjusted offset. So you have as before the formula SL divided by S minus, so you have this extra terms here, Q times H plus L1. So now what is L? So L is the distance between the signalized intersections of the two signals. So it's L equals 200 meters. S is the speed, or it is also called as the thing progression speed. Sorry, the data is here. It is called as the desired progression speed, and you converted it into this 12.5 meter per second. Next, you have this Q, which is this queued vehicles per lane. This is Q, and this is given as 2 in the previous problem. So 2 vehicles per lane. And next you have this is vehicles, sorry, and you have saturation headway. that small h, and that may be taken as 2 seconds per vehicle. Startup loss time. It's your L1, which is 2.5 seconds. So now it's very simple. So your T adjusted, it's L, which is 200 divided by 12.5 minus Q, which is 2 times H, which is also 2. Then you have L1, which is 2.5. So this gives you 200 divided by 12.5 is 16 minus 4 plus 2.5, that's 6.5. So that's, I think, gives you 9.5 seconds. So that's your T adjusted. So let me check if anyone got it correct. 9.5 seconds. Okay, yeah. Value of, yeah, L is 200 meters. That's fine. Okay, so let's get into the next problem, and this is also again related to that problem data that we have already. So I'll write it down in the next slide. So the bandwidth capacity in vehicles per hour. So they were asked about this, right? In primary direction. So I think again it's directly related to the slides. If you need the data, it's here. I'll just show it here. So this is the original data that you have to the problem. So it's basically finding out that bandwidth capacity CBW term, and it I think requires you, let's see, um, so cycle length is not needed, saturation headway is also kind of needed. Then you need this case. That's, I think, pretty much it. Yeah, you were also given the this 36% as the bandwidth efficiency. So considering the primary flow only in one direction having two lanes, the bandwidth efficiency is given as 36%, and you have an expression of this BW by C from there. Number of lanes you know and the saturation headway you know. So from that you have to find out the final answer. Okay, so let's see. So let me check any answers to this. Okay, still no answers. Okay, but let me write down. So you have this bandwidth capacity, which is CPW, and from the slides, the formula for this is 3600 times PW times NL divided by this C times H. Now, let's look at these terms one by one. So this BW by C, this term is directly related to the bandwidth efficiency that was talked about in the, I think, previous slide. So let me also write down. So this is given as, so bandwidth efficiency. So bandwidth efficiency is nothing but this BW divided by C. So this is 36%. That means it's 0.36. So in the slides, I think there was something about 50-50 splits, and that's why this value on that problem, I think it was taken as 0. I think 25 or something. Yeah. But here the sorry, it was taken as 0.5 in terms of that 50-50 split at all intersections. And here it's given directly as an efficiency, so you can directly use it as 0.36. Then you have number of lanes. Here is NL as 2, and saturation headway you already know, H is 2 seconds, I think, 2 seconds per vehicle. Now this will give you the value of CBW. Okay, so this is 3600 times, so I write BW by C, which is 0.36. Then you have 2 lanes and divided by 2 seconds. So it's 3600 times 0.36. That would be your final answer. So let me calculate. Yeah, should be 1296. Check. Yeah, should be 1296 vehicles per hour. So the units are fine because this is because of conversion to vehicles per hour. This is fine. Okay, this is lanes seconds per vehicle. Yeah, this is correct. Okay, did anyone got it right? Okay. Next is, see if anything else is relevant here. I think in the assignment there's something related, but not exactly the same. Okay, so I think that common data problem for question 6 to 10. So there you have two signals. I think those are distanced at 300 meter. Assume that vehicles arriving at your upstream intersection are already in progression at the initiation of the green. Okay. Desired progression speed is given in 15 meter per seconds. So you don't have to do any conversions. So that's good. Saturation headway is 2 seconds per vehicle. It is desired to establish offsets between the signals for signal coordination. Considering the primary flow in one direction having two lanes, cycle length is given, effective lane is given. So it is the ideal offset between signal A and B, assuming that vehicles arriving at the upstream intersection are already in preparation. Okay, so it's the first problem I think that we solved. So that ideal offset is L divided by S. So I think in this problem it's straightforward. It's very easy. Sixth problem is easy. Seventh is, let's see, primary flow in one direction having two lanes. As a bandwidth efficiency is given. Estimate the bandwidth capacity. So that's the last problem that we have solved. So number of lanes are given as 2, cycle length is given, but I think that's not required here because the efficiency is given directly. So that's yeah, here it's I think 0.5, and saturation headway is I think given as 2 seconds per vehicle, so that's safe. Yeah, so I think this is also simple. We should be able to get it. And then I think there is something about reduced bandwidth. So a current coordination plan for propagation speed of this is implemented at signal A and B. If the vehicle speed reduces to 12.5 meter per second, then the available bandwidth, that is the reduced bandwidth is what is that? So maybe let's solve that problem. So a current coordination plan. So for a progression speed is given. Is implemented at signal A and signal B. So if the vehicle speed reduces to say 40 per h, then what is the available bandwidth or the reduced bandwidth in seconds? So how do you solve it? So you can take a look at this and I'll probably solve it in the next slide. Meanwhile, let me see if how many are what are the next one? Okay, so it's been okay, so next one is also related to this. What is the resultant bandwidth capacity due to reduction in say propagation speed? Okay, so let's see how we can solve this. So what you have is so basically you have to find the ideal coordination plan for the current situation, and then you have to come up with the difference that you are having and what is the bandwidth in that case. So let's see how we can solve it. Okay, effective green is given, I think. Let's see. In this problem, is it given? Okay, here you don't have it, right? Yeah. So you need the cycle length as well as effective green to solve this problem. So I'll add it here. Assume cycle length 60 seconds, effective time of 30 seconds. Okay, so that should give you the overall, I think, data that you need to solve this problem. See what is there in the assignment. Yeah, so the effective green and the cycle length were given. And okay, so what you have to do is, let's see. You have two signals A and B, which are 300 meters apart. First vehicles start 0. Okay, have distance from signal. Right, divided by okay. Divided by 12.5, is that? Let's check. Oh, okay. Propagation speed. Okay, so what basically you have to do here is, so you have two speeds, so let's write it down in the next slide. So one is the current progression speed, which is 45 kilometers per hour, which is 12.5 meters per second, as calculated before. Yeah, it's 5 by. Next is you have, because of the reduction in the speed, so you have updated vehicle speed or progression speed, whatever you call it. It's 40 km per h, which is 40 divided by 3.6 meter per seconds. So that gives you 11.11 meter per seconds. Now what you have is that because of this speed reduction, your bandwidth will also be reduced. So you have, let's see, platoon progression. Okay. So in the first case, so let's maybe draw a table. So you have the tone progression. Okay, clean start times 16. Okay. Seven, okay, three, just does anyone have an answer to this? I'm just confused about one thing. Seven, this is 1296 vehicles per hour. Okay, that's previous. Q7 EFFPW is 0.5. Is that okay? Which one? Yeah, this is done. Yeah, this one I'm currently in, and maybe I'll solve this one after that. But yeah, a little bit confused about this. So I think you have to have similar tables created that you had in the class. So let's try and do that fashion. So you have signal A and B. Let's forget about C for a moment because that's not asked in the question. So 1, 2, 3, 4, 5, 6, 7, 6, and then 2. So here you have to have this signal. This is distance from signal, say A. Then you have first vehicle green start, last vehicle green end. Similarly, for the next platoon progression too, you have first vehicle start, and here you have last vehicle green end. So let's solve it, see how it comes. Oh, right. So here it's distance from signal A is 0. First vehicle's green starts at 0. Last vehicle's green end at 0 because the effective green is 30 seconds. The cycle ends at 60 seconds, so this is 60, this is 90. The next one will be 120, 150, and so on. For the next one, which is B, then we'll have this distance is this is 200 meters, I think, in this example. Yeah, so this is in meter. Then you have first vehicle's green start. Now this is nothing but just a division of this 200 divided by this 12.5 in the first case. So this is 200 divided by 12.5, that gives you 16. Then you have for the next one, again you have this 30 seconds gap. So this is 46. Then this will be 76 and this will be 106. The next one is kind of repeated like that. Okay, so the ideal offset, I think it's something we calculated it, right? What was that? 32 seconds. Okay. Full screen. The bandwidth in the first case was this is okay. Bandwidth efficiency is given as 36%. In fact, it can be, I think, found directly from EFF BW as well. Let me just check the assignment. Okay, set given. Okay, it's a slightly different problem. Okay, this is 50% here. Let me see for this problem. 300 meters, 15 meters per second. This is 60. This is 0.5. Saturation headway here is 2. Okay, for this problem, it in assignment, you just need to have the bandwidth efficiency, and from that, I think you can directly get BW by C as the efficiency, and so that's I think that value is 50%. So it will directly give you the answer. It's very simple in this case. So I think because I took kind of a different kind of problem data, so I was trying to get to the answer, but it was not the correct way, I think. So I think the easier way of would be doing it. It's yeah, this could be one approach, but uh, the direct approach could be this just getting this bandwidth value, which is BW/C into 100. So if it is given as 36%, you can directly use that here in this problem. So maybe I'll just try to connect it with the other method that was used in the class. But it's very simple for the assignment problem. It's just you have to apply the formula. Here also it's once you have the BWC values, you just need to find the resultant bandwidth capacity with the formula that you have. And that's again directly related to the previous problem that we have solved. You know NL, H, BW and C, it's straightforward to calculate it. Okay, so I think this is fine for this discussion, but for the other problem, I'll check how to solve it. Uh, let, let me check. So if the vehicle speed reduces, actually, I think I can look at the assignment problem and connect it to that. So it's 15 in the assignment problem is 15 and 12.5 and uh, 300 meters for the distance. So that's 300 divided by 15, which is 20 seconds. And then you have 300 divided by 12.5. The next case it is 24 seconds to go there. See, here the first vehicle is at 16. So this is signal is turned green here. Here also, okay, so this part is fine. For B is vehicle, okay. are your ideal offsets. Now, to the third one, I think it was 32 seconds. I see. So in the other problem in the assignment, it was simple. It was between two signals, A and B. Here we have three signals. So that makes the problem a bit complicated. So ideally, I think I framed the question wrong. I think that's why it happened like that. So it's typically, I think you can add it between signal A and C. Um, that should give you some indication. So for C, I think it would be 32. That's your ideal offset. And well, second, calculation of anyway, maybe let's not make it complicated, or I'll probably get back to it in the next class because it's anyway feels confusing. So let's maybe I'll just put a note here to be solved next class, or once the assignment solution is released, I think you'll get an idea of how to solve it for two, and this extension would be easier. For now, maybe just skip this discussion and go for the remaining ones. I think for two signaling, uh, it's easy to get the solution. So it's only when there are three that there are complications, and you have to look at how it is solved in the slide using the diagrams that were drawn there. But anyway, if anyone got it correct. Okay, so this is 26 seconds. So is it? I thought the answer would be 30 second. Uh, okay, 26. I don't know. I think it should be 30, but anyway, the next one is the capacity you have to calculate. Yeah, capacity is direct formula. You have to just apply it and that's all. Yeah, here it's I think 300. This is, this is it. Yeah, this is fine. Yeah, maybe it should not be 26. You can check. Okay, so the last one is I think again solved because it's again directly related to what we discussed so far. It's adjusted offset. So that's fine. So let's see what is remaining. The first three discussed and this is discussed. Okay, so there are no numericals as such. Maybe just solve some of the remaining ones. Uh, Not all of them, but some relevant ones that were there. Anyway, so problems I'll just mention. So let's see what we can have. Let's open the assignment. So let's maybe start with some true and false. So the first one would be, say, this advanced coordination system requires the practitioner to define consistent cycle length for the corridor, as well as splits and offsets for each timing plan. So that's one. Next is shorter travel time between signals results in greater vehicle platoon dispersion. Okay, so the actuated phase will terminate if the Gmax for that phase is achieved. Next is actuated signals have variable phase sequences but cycle length remains fixed. Next is for semi-actuated operation. Actuated phases are used to serve the minor formats. And passage time should be designed such that straddling vehicles may not regain the green. Okay, so let's stick to this for now, and I'll add more on the next slide. Okay, so the first one is advanced coordination system requires the practitioner to define a consistent cycle length for the corridor as well as splits and offsets for each timing plan. So this is true. This parameters needs to be adjusted based on the measured conditions. The first one is true. I think you'll find it related to, I think, in the slides as well. Yeah. Next is shorter travel time between signals results in greater vehicle platoon dispersion. So this is it true or false? Shorter travel time. Let's see if anyone answered it. So without explicitly defining the specific areas for cycle length, first one is true, second is false because platoon value is less. Yeah, true. 356 is true, you're saying. Okay. Second one is false, that's correct. And the reason is also correct that there will be kind of less opportunities for drivers to deviate from the average travel time and so on. So the dispersion won't be there, so there will be lesser dispersion. And next is actuated phase will terminate if the Gmax for that phase is achieved. So that's true again. That's again related, I think that was discussed in the class. Actuator signals have variable phase sequences, but cycle length remains fixed. So now, so this should be false. Cycle length can vary actually. Next is for semi-actuated operation, actuated phases are used to serve the minor movements. So now for semi-actuated operation, so the controller is kind of programmed to dwell with the non-actuated phases, so displaying green for at least for a specified minimum duration. So this is true, and passage time should be designed such that the straggling vehicles may not regain the green. So that is yeah, these are from the slides itself. So this is fine. Next is I think we can solve something related to this, CY. Okay. Yeah, let's solve one more. So it says, I think it is also there in the assignment. So the two-way total our traffic volume between two intersections, which are 20 meters apart, is 4250 vehicles per hour. So which of the following statements is true? Are correct with respect to variant model coupling index. Options are the value of Ci equals 13, therefore signal coordination between intersections can be considered. Next is P, so this is the value of Ci equals 13, therefore signal coordination between intersections is desirable. C is the value of Ci is 0.88. Therefore, signal coordination between intersections is not required. Is not required. Finally, the value of Ci is 1.41. Therefore, signal coordination between intersections is desirable. So as you know, as you can guess from the problem, you have to find the Ci value and then get look at the range. So to get the coupling index, you have a formula. So that was there in the slides, and it takes into account this thing. Let me check quickly. This is the formula is uh, depends on what kind of models you have. So in general, for two signalized intersections, it's V by D. I think V is two-way traffic volume in peak hour, and D is the distance between the signals. So here, if that can be applicable, but there's something about variant model. So that is asked in the question. So for that, it's V by D square. And for variant Ci, the ranges, depending on ranges, whether no coordination is required or coordination is desirable or can be considered, those things are defined. So here, for the variant model, the Ci is V divided by D square. V is 4250, so that's volume, and you have this D, which is 920 meters, but I think you have to convert it. So this 2/8 total traffic volume peak hour divided by 1000 you have to do anyway, and then this D you have to convert it into miles, and after that only you can find out the value. So you have to be wary of the units here, or yeah, the units that are mentioned. So this part is divided by 1000, so this corresponds to the meter. And then for the D, you have to convert it into miles, and 920 meters. So you have, let me check, 920 meters equals how much mile? Okay, it's around 0.57. Now you have to just divide it by 0.57 square. So that will give you the Ci value. Let's check the Ci value. So you end up with close to 13. It's 13.08. So yeah, that's fine. So here the first two options can be true. So the CI value is 13, but now we have to go for the additional checks. And for the variant CI, so you have a table which tells you between 1 to 50, you have to consider coordination. So the signal coordination can be considered. So that would be the right answer. So the answer is correct answer is A. Okay. So let's see what was there in the assignment. Is it so I think in the assignment also similar problem is asked where as per the coupling index for two adjacent intersections located at 1,000 feet apart. So that's given in feet, you have to convert it into miles. And having two-way traffic volume of that's given peak volume. So the signal coordination is whether desirable or not. Is it true or false? You have to find out. And this is not the variant model, so I think the formula would be V by D in that case. So you can get it. That's not a problem. Yeah, so assignments, I think first 10 questions I mainly discussed, and the later ones I think we'll be able to answer. But anyway, let's see how much I can cover in the next 15 minutes. Yeah, the fourth one is I think again was about true false and directly from the slides. So I think I've already discussed one of them, or yeah, I think two of them were part of that question anyway, so I think you'll be able to answer it. Okay, let's see what's remaining. Okay, so this one I think I haven't solved. Yeah, let's get into one more true false type thing. Okay, so the first one is random vehicle arrivals at each intersection are desirable for the coordinated system operation. Next is longer cycle lengths may result in vehicles in turnways to back up into through lanes. Next is shorter split times may result in unmet demand during the cycle. Then you have force of is the time at which control is returned to coordinated cases. Okay, I think these are also directly from the slides. So let's see what could be the answer to this. Does anyone have an answer? False. Okay. BCD is true. Yeah, that's correct. This is true. Sorry, this is false. These are true, and this is again directly from the slides itself. Okay, maybe going to another problem. Let's see what's remaining. So there is a matching type problem, I think. So that's about progression, like flexible progression reverse, alternating simultaneous. So that's, I think, direct definitions and characteristics. So that's, I think, easy. Yeah. Next is, I think there is something about which one of them is true about vehicle platoon dispersion. Yeah, I think that's again easy to answer. And something about pre-timed signal control and not the characteristics of it, that's fine. Then you have another matching type about this oversaturation symptoms. That's, I think, mitigation strategies. So that's towards the end. And then this various approaches to grouping in intersections. So that's matching type another. And final one is about this critical cycle maximum allowable headway. These are from the initial portions of the discussions, I think. Okay, maybe I'll just have similar thing discussed and wrap it up in the next 5-10 minutes. So let's maybe take one matching. Let's see. Which one can take. Let's take about the progression one. Q9. Yeah, we had a discussion, right? Q9. Yeah, so there is an issue. That's fine, right? You just find out the reduced bandwidth from here, or the available bandwidth, whatever it is, this VW, plug this into this. So you have that formula VW by C multiplied by, I think, 3600 and divided by, I think, that headway. So it's easy, right? You can get it. And you have to multiply it with the number of lanes as well. So all the data are given. It's easy. You can get it. Yeah. Formula is the same, right? It's written in the slides 3600 times BW by C times NL divided by H. That should be the formula. Let me quickly check and confirm. Yeah, I think same formula that's there in slide, I think 52. Yeah. Related example, I tried to give a 3, but that didn't work out. But with 2, it's fine. It's the same formula, right? Here I have already used it. This is the formula. It's written in the slides, right? BW you calculate from the question number 8. NL is given, C is given, H is given. Just plug those in, you get the solution. Like this much you have to do, right? I cannot just give you the answer. Okay, maybe finish with one matching thing, and then that should be it for today's discussion. Okay, so let's wait. This column X, column Y. This double alternating regression. This is reverse progression. Simple progression. Simultaneous progression. Is downstream signals. Selects between green, green, red, red, green, red, red, and so on. This is used for very closely spaced signals or for rather high vehicle speeds. And will offset is negative, and D is green wave advances with the vehicles. Okay, so what would be the answers to this? Okay, so is double alternating progression. So let's think A, okay, was reverse progression. Okay, progression. Then you have simultaneous. Okay. Get an answer. ADCB. Is that correct? Answer is 7200 for Q9. Yeah, maybe, but I'm not giving you the answer. So ADC, what did you write? ADCB. Is it correct? Let's check. Okay, let's take simple progression. So a simple progression, green wave advances with the vehicles. So this is D. Uh, you wrote 2 is D, which is wrong. Next is reverse progression. Let's take that. So here for reverse progression, you will have, I think, ideal offset as negative. Let's see. Yeah, so it should be 2 should be C. Then you have 1 double alternating progression. Here, so it's the first one, that's correct. So that leaves us with 4, which should be B. Simultaneous progression, very closely spaced signals, that's correct. So it should be ACDB. Uh, yeah, ADCB is wrong. Okay, so yeah, it's almost time, but yeah, that problem Q9, I'm not giving you the answer. You, if you solve this one, you will get this one as well. It's direct application of formula, so uh, that should be it. So it's 0 point, okay, 1800, but anyway, let me quickly check. Okay, I have to check the units and everything. This I didn't work it out, but yeah, it may be 7200. I don't know, but yeah, it's all. Okay, so it's 9 p.m. already, so I'll probably stop the session for today. So yeah, hope you'll be able to answer the assignment problem. So it's not like I'll solve every assignment problem in this session because you have to do something as well. And you will also like know the answers once the answers are published later on. So yeah, wait for that. And till then, like you have to take it upon your own and solve. Q5. Look, I solved a similar problem. I cannot give you every answer, right? It's you have to work it out. Go through the slides and do it. So it's not like I'll just tell you the answer. If you have understood the other problem that I solved, you will be able to have solved this one as well. Yeah, I'll suggest just go through the slides and solve it on your own. It's not like I'll just solve everything for you. Yeah, these are all from slides itself. You'll find it. It's just do it, put some effort and get it done. Show me similar problem. Similar problem I just solved in the slides. Slides will anyway be shared after this session, so you don't need to take screenshots or anything. This is the one I solved, right? This is very similar to what was given there. Okay, maybe that's all. Yeah, so it's 9 already, so I'll close the session. So see you all next week. Yeah. CI equals, that may be the case. Just go through the slides. I cannot give you all the formulas, right? It's there in the slides. Like, it's not like I may have to just solve everything for you. Okay, but anyway, best of luck with your assignment. Go through the slides and solve it. So see you all next week. I'll close the session for today.